Hypersonic missiles aren't just faster missiles. They represent a major shift in how military power is being projected. Now, when people hear hypersonics, they immediately think speed or even things like invulnerability. But speed alone isn't the story. The term hypersonic is generally defined as anything above Mach 5 or 5 times the speed of sound. And here's the part that most people miss. Mach 5 or hypersonic speed isn't new. It's not even close. As far as space is concerned, Mach 5 or hypersonic is actually slow. Ballistic missiles have been hitting hypersonic speeds since the early rocket era, going back to World War II. So this isn't some brand new physics breakthrough. What's new is the combination of speed, maneuverability, and advanced targeting systems. Now that combination changes strategy and it changes doctrine. It changes warning times. And that's why everyone's suddenly talking about it. And that's why we're taking a closer look today. My name's Richard and welcome to Ron's Industries, the industry blog for investors where we're pro-wealth, pro-growth and pro-tech. And this time in the tech industry, we're looking at why hypersonic weapons suddenly matter. Now let's clear something up. Flying at speeds above Mach 5 has been happening for decades. Air-to-air missiles like the AIM-54 Phoenix reached around Mach 5, and that's a system that's already been retired. Russian systems like the R-37 also operate in the hypersonic regime. In fact, pretty much any air-to-air missile launched from a high subsonic or a supersonic aircraft will likely be hypersonic at the end of its boost phase. But of course, ballistic missiles have reached hypersonic speeds for decades. And once you understand basic rocket physics, it's actually not that surprising. With solid rocket motors and high propellant mass fractions, say about 50% by weight, hypersonic speeds are almost guaranteed. So again, the speed itself is not revolutionary. What matters is what the weapon can do while it's moving that fast. Now, before we talk about traditional ballistic missiles, rocket artillery systems and tactical ballistic missile systems with ranges of less than 300 kilometers already have peak speeds of about Mach 3. And these are the smallest missiles in the defense portfolio. Speed only gets faster as you go higher through short range and then to medium range ballistic missiles with speeds probably in the order of around about Mach 10. Intermediate range ballistic missiles and intercontinental ballistic missiles reach hypersonic speeds during the boost phase, often within the first 60 seconds of flight. And by terminal phase, terminal velocities reach Mach 15 through to Mach 20, or sometimes even higher. In the case of ICBMs, re-entry speeds exceed Mach 20. Now to put that into perspective, the final rough 90 kilometers of ballistic flight made up of around about 45 kilometers in altitude and 75 kilometers in lateral distance can be covered in as little as 14 seconds, which is an average speed of Mach 17. That's how fast we're talking. Predictable trajectories. Once the payload is in ballistic flight, the math is set. That predictability is the only reason missile defense is even possible. They're incredibly fast, but they're not agile. And that's the difference. Now here's where physics starts to push back. At 75,000 feet, air density is only around about 5.5% that of sea level. Now that's not space, but aerodynamically it's starting to get close, which means that without thrust vectoring, maneuverability is extremely limited. And at extreme speeds, at Mach 20, you're covering roughly 6 kilometers per second. And at those speeds, even tiny errors in guidance is going to be mission failure. So if you want maneuverability or accuracy at hypersonic speeds, you need an entirely new control solution. That's one problem that modern hypersonics is solving. Now, the real breakthrough isn't speed, it's maneuverability during hypersonic flight. Now, if a projectile moving above Mach 5 can change direction mid-flight, air defense becomes exponentially harder to achieve. And that's where we end up looking at two different types of hypersonic vehicle. Now, firstly, there is the HGV, or the Hypersonic Glide Vehicle, launched by a rocket, same way as a ballistic missile, before it separates. Now, instead of following a predictable ballistic arc, hypersonic glide vehicles will have specific and classified flight profiles. But in general, we're talking about generally gliding and carrying that speed forward. But most importantly, hypersonic glide vehicles can alter their trajectory mid-flight. Now, as I said, exact profiles are classified for obvious reasons, but even limited maneuverability breaks interception assumptions. Now, every time a hypersonic glide vehicle maneuvers, it's going to lose energy, especially since it's unpowered. So those maneuvers aren't unlimited. But even a handful of unpredictable corrections can compress response times dramatically. Now, this is where things get really interesting, because secondly, we've now got hypersonic cruise missiles that remain powered throughout flight, typically via scramjets. Now, unlike glide vehicles, hypersonic cruise missiles can sustain their speed. They will typically fly within the atmosphere at speeds of Mach 5 or higher. And now we get to the strategic problem, and that's what we call the radar horizon. A ballistic missile at 200 kilometers in altitude is visible from roughly over 1,600 kilometers away, which is going to give a fair bit of detection time. A hypersonic missile flying at 100 meters in altitude has a radar horizon of only 35.7 kilometers, as in, that's the earliest or the first point that you're going to detect it. Now, at Mach 5, at only the minimum speed of 1,715 meters per second, that 35.7 kilometers is crossed in only 21 seconds. If we go to Mach 10, we're looking at around about 10 seconds. Now, that's not a lot of time to decide what to do. That's barely even time to recognize that something's coming. And this is why hypersonics matter. So let's talk interception math here. Interceptors ideally should be faster than the target that they're intercepting, or they should have enough fuel or energy to sustain pursuit. But in truth, nearly no intercepts are done purely from pursuit or from the chasing perspective. All the same, not every intercept is going to be directly from head-on. We'd expect nearly all interceptions will be from lateral or at least the sideways path in some component. Now, imagine a hypersonic cruise missile banking away by 30 degrees at Mach 5. In the space of just 10 seconds, that would force the interceptor to have to travel an additional 8.5 kilometers in extra distance. Now, here's the issue. The interceptor boost phases are extremely short, often in the order of around about 30 seconds, which in many cases would give, say, around about 30 kilometers of powered flight. After that, the interceptors could be gliding simply on stored energy. So if a hypersonic weapon can keep forcing geometric distance changes, it can drain that interceptor's energy budget. And that's how speed plus maneuverability breaks traditional interception doctrine. Hypersonics compress detection to decision timelines. Now, in some cases, we're talking about 10 to 20 second windows in some scenarios. Now, that forces a rethink of early warning systems, sensor networks, interceptor geometry and planning, as well as defense doctrine as a whole. And they're especially dangerous against time-sensitive targets, say an aircraft carrier in the Pacific Ocean. Now, that's why militaries are scrambling. So scramjets enable sustained hypersonic atmospheric flight. Now, they've got no moving parts. They actually use forward motion to compress incoming air in order to operate efficiently above Mach 5. The second technology that we really need to look at is thermal protection. Hypersonic flight generates extreme heat, and this isn't something that's new. The SR-71 Blackbird engineers already knew heat was the real enemy just for sustained speeds at only Mach 3. At hypersonic speeds, leading edges experience enormous thermal loads. Advanced heat shielding and materials are going to be absolutely mandatory. Even re-entry vehicles experience massive heating for the final 80 to 90 kilometers of descent. Now imagine maneuvering during that, because this is the real challenge. The guidance and electronics. Traditional GPS may not be reliable at hypersonic speeds, and certainly shouldn't be relied upon in a high-threat operational environment. Navigation systems are primarily going to be inertial navigation, potentially satellite-based, or even have star maps. Potential AI-assisted targeting would be in the final phases. But electronics must be able to survive those extreme temperatures and vibration. Consumer electronics only worked at temperatures of maybe up to around about 60 degrees, while surface temperatures could be well in excess of 1,000 degrees on a vehicle that's doing hypersonic speeds. Programs like the X-15 already showed how brutal hypersonic flight is on different materials. Materials such as fiberglass, Kevlar, quartz, as well as metals and other ceramics are all going to have thermal limits. So that would mean that radar guidance behind something that would fail would not be an option. Guidance at Mach 5 with a plasma sheath is cutting-edge engineering, to say the least. Now, we've got to understand, when it comes to hypersonic weaponry, this stuff is already happening. Russia already fields weapons such as Avangard, as well as the Zircon hypersonic cruise missile. China has the DF-17, the DF-ZF, as well as the DF-27. The United States is developing different platforms such as the AGM-183 Arrow, as well as the long-range hypersonic weapon. Now, these aren't theoretical. These systems are being fielded, and the focus isn't just nuclear. We're talking about conventional deterrence, something that can change the military calculus altogether. So hypersonic speed alone isn't new. Maneuverability, precision, and survivability at hypersonic speeds, that's what's new. And it's enabled by technologies such as scramjets, advanced materials, high-temperature electronics. And these technologies are going to influence warfare, defense spending, and strategic stability, potentially for years or even decades to come. But here's the reality. As certain as hypersonics are changing the battlefield, the next generation of weaponry is certainly already in development. Now, I hope that you found this useful, and I'll see you in the next video.